Hello everyone, my name is Chanda Kumari and I am from EPH. And today we will discuss about Fourier series. So let's start it. So first we will discuss about the introduction part of Fourier series. So for that I have written two definition of Fourier series here. Let's see one by one. So first one is like a Fourier series is a periodic function composed of harmonically related sinusoid combined by a weighted summation. And the second one is like uh, a Fourier series is a way of representing a periodic function as a sum of sine and cosine function. It is analogous to a Taylor series which represent function as possibly infinite sum of monomial terms. Let's go to next slide. So let's see the history part. So there was a scientist named Baron Jean-Baptiste Joseph Fourier. He introduced the idea that any periodic function can be represented by a series of sine and cosine which are harmonically related. So let's go to the next slide and talk in detail. So now talk about its generally written form. Like if you have a fx with time period t and fx is defined here that this is a Fourier series, like then how we would write it. So we would write it in the form of fx is equal to a naught by 2 plus summation of ak cos 2 pi k x divided by capital T, where k will go from 1 to infinite, and plus summation of bk sine 2 pi k x divided by capital T, where k will go from 1 to infinite. Here capital T will be is the time period of periodic function, and the a naught, ak and bk is the Fourier series coefficient, and the individual term in the Fourier series are known as harmonics. Okay, like if we are giving the different value of k for the fx, then we will get a different fx, so that different fx is called harmonics. Now let's see the calculation part of its coefficient. And so here we can see that to find the coefficient an, we will start with the synthesis equation of the Fourier series. Xct is equal to summation of an cos n omega naught t, where n will go from 0 to infinite. So after calculating, we are getting here like half of summation of an cos m minus n into omega naught t into dt. So basically we have to integrate only cos m minus n into omega naught t dt over one time period capital T. So in next slide I have written something like this. Like when m is not equal to n, then the integration will be 0, and if this will be equal to each other, then that what does that mean? M minus n will be 0, so cos 0 will be 1. So then here we will get the integration is like 1 into dt over one time period capital T, and so we can calculate t. We can integrate here dt, so we will get here capital T only, and then after putting in the back uh, integration form, so we will get like this: xct into cos m omega naught t dt is equal to half of am into capital T. So what I have written, like if n goes from 0 to infinite, every term in the summation except when m is equal to n will be 0. So the only term that contribute to the summation is m is equal to n. So that is why the entire summation reduced to half of am into t. So from here only we can calculate a value of am. So after calculating am, earlier we had to find an, so simply we can replace m with n, and here we got a result for an. And also we had to calculate a naught, where n will be 0. So after putting n is equal to 0, we are getting 2 by t integration over xct dt over one time period capital T. And same as we can find out the value of bn, and here we have to take the different function in initial, like x naught t is equal to summation of bn sine n omega naught t, where n will be from 1 to infinite. And so from here we can get the value of bn. Now let's see the complex form of Fourier series. So we already know that cos theta is equal to e to the power I theta plus e to the power minus I theta divided by 2, as well as sine theta is equal to e to the power I theta minus e to the power minus I theta divided by 2i. So from that formula, using that formula, we can write the Fourier series of the function in complex form like this. And after the calculation, we will get the Fourier series in the form of complex form. It will be like Cn e to the power I n z, where n will be from minus infinity to infinity, and where here we have used the following notations also. C naught is equal to a naught by 2, Cn is equal to an minus ibn by 2, and C minus n is equal to an plus ibn by 2. The coefficients Cn are called complex Fourier coefficient. They are defined by the formula Cn is equal to 1 by 2 pi fx e to the power minus inx dx over with integration from minus pi to pi, and here n will be vary like we can take the value of n 0 plus minus 1 plus minus 2 and so on. Now let's see the Dirichlet condition. This is basically the condition for any function to be uh, in Fourier series. Like if we have a function, then can we write it in form of Fourier series? So that is this condition called. So in mathematics, the Dirichlet conditions are sufficient condition for a real valued periodic function f to be equal to the sum of its Fourier series at each point where f is continuous. So there is three conditions written over there. First one is like f must be absolutely integrable over a period. Second is f must be bounded variation in any given bounded interval. Third is f must have a finite number of discontinuities in any given bounded interval. And the discontinuity cannot be infinite. It should be a finite number. Now let's discuss about the types of Fourier series. So basically there are two types of Fourier series. These two types are basically the representation of Fourier series. Like if we are representing in the cos and sine function, using cos and sine function, then that Fourier series will called trigonometric Fourier series. And the if we are using exponential form, then this Fourier series will known as exponential Fourier series. So let's discuss about the graphical representation of Fourier series. Here I have taken the function is a sine function. So when we will write it in form of Fourier series, fx is equal to a naught by 2 summation of a n b cos n omega naught t over n will go from 1 to infinite plus summation of bn sine n omega naught t, and n will go from 1 to infinite. So then this fx, this graph which I have shown, is the representation of this fx. Now let's discuss about the properties. So there are several properties. Let's see one by one. So first is the linearity property, in which we are taking two functions xt and yt, and they have fxn and fyn Fourier coefficients. So according to linearity property, it states that axt plus byt, if we are taking this function, then the Fourier series coefficient will be like a fxn plus b fyn. And another property is time shifting property, in which if we are taking the function xt and then if we are shifting the timing, like t will replace to t minus t naught, then what is the effect in coefficient? Then if we are doing time shifting, then time shifting property states that its coefficient, Fourier series coefficient, will be like e to the power minus j n omega naught t naught times the initial Fourier series coefficient. Let's discuss about the another property, frequency shifting property. In this, we will simply shift doing shifting in the frequency. So after the shifting in frequency, we are getting its coefficient like only the difference in n, which will be n minus n naught. And another property is time reversal property, in which we are just simply reversing the time, like t will become t minus t. So then time reversal property states that if x of minus t, if we are taking function, then their Fourier series coefficient will be like f of minus xn. And another property is time scaling property. Here we are simply scaling the timing, like we are multiplying some constant with the time. So first we had taken xt function, which has Fourier series coefficient fxn. Now we are taking function x of at Fourier. So then time scaling property states that if we are doing time scaling, then the coefficient will remain same, but time scaling property changes frequency component from omega naught to a omega naught. And the other property is the differentiation and integration property. If we are differentiating any function, then their coefficient will simply get multiplied with j and omega naught with the initial coefficient. And if we are doing integration, then it simply get divided by j and omega naught. Thank you.